Hello students, today I am going to discuss Parseval's theorem. So if we have a periodic function defined in interval minus L to L, and this function is periodic fx plus 2L fx, then the periodic extension of this function, Fourier series of this function is given by this expression. Now, what is Parseval's theorem? Parseval's theorem says if I know the Fourier series of a function, then I can calculate the square average of the square. That means you have function fx. If I take a square, the average of the square is the average of the square function or mean square of the function. Then this is equal to a0 square by 4 plus half summation an square bn square. Now, what is an, bn, a naught? They are the Fourier coefficients. So, if I know the Fourier series, I can immediately find the square of the average of the square of the function or mean square of the function. And sometimes this 2 will not be there. So, this will become 2, this will disappear 2, and you can take also under root. Okay. If I write mean square, RMS value, okay, RMS values of the function can be calculated by using this expression if I know the Fourier series of the function. And now the proof of this theorem is very simple. So we have, so for this, I'm defining two periodic function. So let us take, let's fx and gx be two periodic functions, two periodic functions, and both are defined in the same interval minus L to L, minus L to L. So I can write the Fourier series of both. So Fourier series of first I am writing constant back this time by say a naught, and I have a series. This is n equal to 1 to infinite. Okay, so this is series here. You have to write n equal to 1 to infinite. So n equal to 1 to infinite, and now you have what you have, say an cos of n pi xl, and then you have bn sine n pi xl. Similarly, I can write a Fourier series for gx that will be c0 by 2 plus n equal to 1 to infinite cn cos of n pi xl plus I write this is a dn sine of n pi x upon L. Now we know values of a naught. We know a naught is what? A naught is your 1 upon L minus L to L fx dx. Similarly, your C0 is 1 upon L from minus L to L gx dx. Similarly, an is your 1 by L minus L to L fx cos of n pi x upon L dx, and your Cn is 1 upon L minus L to L fx cos of n pi x upon L, and your here Bn is 1 upon L minus L to L fx sine of n pi x L dx, and your Dn is 1 upon L minus L to L gx. Here you have for A and C, this is G. Gx sine of n pi x upon L. Okay, so this is thing. Now I can use these coefficients. So now we have the function, say for fx a naught upon 2 plus n equal to 1 to infinite an cos of n pi x upon L plus Bn sine n pi x upon L. Now just multiply this function with gx and integrate with between minus L to L. So if I multiply this function fx with gx and I integrate with minus L to L, this gives me a naught upon 2 multiply with gx. So that is minus L to L gx dx plus n equal to 1 to infinite a, and I'm multiplying from gx, okay, and gx cos of n pi x upon L, and similarly here I'm writing here integration bn is also there, bn minus say minus L to L gx. I am putting an out of the integration because integration is from x for x, not for n. So dx gx for sine of n pi x upon L dx. Now we know this. What is this one? This is your C0. C0 just now we have seen what is C0. C0 is 1 upon L minus L to L gx. So this is my A0 C0 by 2 and this is C0L. Okay, because 1 by L is C0 C0L. Similarly, if I write this one n equal to 1 to infinite gx, this is my gx cos, this is my cn. So this is my an and this is my L into cn. L into cn. Similarly, this is my bn and this is my dn. L into dn. So L into dn. 1 by L will be there. Okay. Now what I can do, I can write 1 upon L minus L to L fx dx is equal to a naught c naught by 2, and then you have n equal to 1 infinite a n c n plus b n dn. So this statement is itself is very, very useful. And now this is fx gx, fx gx dx. Okay. Now I put if fx is equal to gx, if I put here, then what will become? This become 1 upon L minus L to L square, fx square dx. And now C0 you have to write the A0, A naught because it's the, both functions are same. Then this become A naught square by 2 plus n equal to infinite an square, and this will become bn square. Okay, and now I can use my usual notation. So if I write my usual notation, I can say 1 upon L minus pi minus L to L, okay, fx square dx is my equal to a naught square by 2 plus an square plus bn square, or if you divide by 2 here, so this become average minus L to L fx square dx, and then this become a0 by 4 plus half of an square bn square, and in usual notation this will be a naught square 4 plus 1 upon 2 a n square plus b n square. Okay, so 1 upon 2l minus l to l fx square dx. So this is my Parseval theorem. Okay, now we'll see some more some applications of this Parseval theorem, and we will also see one of the another form of Parseval theorem when the series is written in the complex form. complex form. Okay, so let us stop here. Thank you very much.